There are many machine learning algorithms, in particular for classification or regression, where you have some data with some input features and you want to be able to predict on a test set. Today we're going to be going through the kNearest neighbors algorithm. It's one of the simpler algorithms for machine learning and also for classification. You can also do regression with kNearest neighbors, but we're going to be focusing on classification, have some pseudocode with an example problem that'll make it more clear, and then some Python code as well to take you through how to calculate this for large data sets. So with every machine learning algorithm, we have three things. The first one is representation. It's the model that we use to be able to calculate the predicted output. The next one is optimization. And in some cases, we optimize parameters of our model, or we optimize the selection, such as the number of k values in kNearest neighbors. Also, we have evaluation, and this often occurs with classification through a confusion matrix or an accuracy score. So we're going to be going through all three of these with the kNearest neighbors example. So in classification, you can see many different algorithms. This is AdaBoost or adaptive boosting. There you can see decision tree, and for each of these you can see the train time, the predict time, the size. Okay, so this is kNearest neighbors, 74 kilobytes, and then the accuracy as well. So one of the issues with kNearest neighbors is that you store all of the points for evaluation for a new point. So it can take a bit of memory, especially if your data set is large. Overall, it's very fast. There really is almost no training, but the retrieval might take longer if you have many data points. All right, and we can see some of these other ones and just how they compare, and their strengths and weaknesses to every machine learning algorithm. Here's random forest classifier, for example. That one takes a lot of memory. Stochastic gradient descent is very fast. Okay, but it's not necessarily the most accurate, especially for low dimensional cases. Support vector machines and others. You can see at the title at the top those other ones as well. Alright, so let's talk about kNearest neighbors in particular. The very first thing is the distance to the input features. That's the representation. So we want to calculate how many points are close to the one that we're trying to test, and then the optimization is the consensus for the closest k points. We'll use the mode of that set. Basically, what is the one that appears most frequently? And then evaluation, it's going to be like a confusion matrix or something like an accuracy percent. Alright, let's go on to the next one and do an example here. Okay, so here is a dog or cat, and these have labels. And I've just put a number of these dogs or cats and labeled them. So you can see the red cats or the blue dogs. And we're going to try to classify them by a single feature, which is the weight of these animals. And so the smallest ones being down here and the largest ones being up here. And most of the cats are probably going to be in this area. Dogs are potentially going to be smaller, but also larger. And there's also some outliers as well. All right, we have a representation is going to be our feature. Okay, the feature is going to be the weight, and then the label, which is the cat or dog. Now we're going to split these two into a train and then a test set. So we don't want to necessarily have these same animals be up here in our training data, because then we'll be matching to those. And we could have just one as part of the test set, and then the other ones use those for training. But let's just split these into 3 right here, and then we'll use the remaining 13 as our training data. So if we have two nearest neighbors, we're going to take the label of those two nearest neighbors. So you can see that this one is classified correctly because its two nearest neighbors in terms of weight are both cats. Now this cat here, its two nearest neighbors are dogs. So this one's going to be inaccurate. We're not going to be able to classify this one correctly. And then this one here is classified correctly. All right, but let's say we had three nearest neighbors. All right, now here we have two cats and a dog, which are the three nearest neighbors. And for this one, we have two dogs and a cat. And so in this case with 3, we're still going to have the same result, and this one is misclassified. But that is one of the things that we can adjust with this algorithm, is how many nearest neighbors we want to use in order to calculate the mode of the result. Alright, so for the confusion matrix, this is the evaluation. And the question is the animal a dog? And the true label, we'll just say 0 or false is the cat, and 1 or true is the dog, and then the predicted label is the color. So this one is misclassified. We have a false positive here, that's a type 1 error. And then we also have a false negative type 2 error, where we said it was a cat, but it was actually a dog. And this one, for the false positive, we said it was a 1, but it was actually a 0, or we said it was a dog when it was a cat. Alright, so the accuracy for this case is going to be 2/3 because we classified 2 out of the 3 correctly and 1 out of 3 incorrectly. Alright, let's go to this code example now. We're going to go through some Python code as well. But let's do our pseudocode first. So the very first thing we want to do is divide the train and the test set. And then we'll select k for the number of nearest neighbors. This is a hyperparameter that we can optimize later. But let's go ahead and just select a value and then test the result. Alright, we have for every test set, we're going to test them one at a time. We're going to calculate the distance to the train features. We'll sort that list to find the nearest k training data, and then we'll take that test set and we'll assign it a new predicted label with the mode of the k training data. And that's going to be the label that appears most often, and that is going to be the mode of that list. Alright, and then we'll calculate the accuracy as well. Okay, so let's go ahead and start. I'm just going to show you the code, but then let's go through it. I'll go ahead and type it out with you. We're going to import this. Now you can just load this in Jupyter Notebook, and it will load this code to produce the data set. So we're going to do that first, and then we're going to divide into a train and test set. Okay, and there's a couple different ways to do that. We're going to be working with pandas data frames, and I'll go through each of these steps with you one at a time and explain them just a little bit more. But I just wanted to show you the code before we get into it. We'll select one test at a time. Alright, and then for every value, every test set, every row in our training data, we're going to calculate the distance, and then we'll sort it, and then create our list, and then finally we'll calculate the accuracy. Alright, and there are two different ways of doing that I've shown, with the confusion matrix from sklearnmetrics, or you could do the crosstab and do it graphically with this confusion matrix. In both cases we had 100% accuracy. Alright, so let's go ahead and jump into the source code, and what I'm going to do is just open up a new Jupyter Notebook, and I want to walk through this with you kind of step by step so that you understand all of the different pieces of this, and we'll just do that together. And I'll make this just a little bit larger so it's a little easier to see. Alright, so let's just call this kNearest neighbors, and I've just selected the name up top to be able to change it. All right, and then let's come to the course website. So if you come to APMonitor.com/PDS and then come down to the kNearest neighbors down here on the right. Okay, this gives a little bit more information about this, and we'll go ahead and just get this code right here. One of the easiest ways to do that is just select Get Code down here on the right, and then just copy that address, and then we'll just do the %load and then paste our address there. And that will just load the code for you. We can then run it with Control Enter. And that will generate the pair plot with the data. Now, one of the things that we can see here with this data is just looking at the distributions from Y, we're able to almost just do a classifier just based on Y. We may not even need X. So you can see the distributions overlap here, but here with Y, it looks like there's just kind of a clean break. So you'd maybe only need one input feature looking at this this pair plot. Okay, but let's go ahead and just use both of these just as an example. All right, I'm going to insert a cell below, and the first thing that we want to do is just split the data. So I have the data here. If I do data.head, or if I do data.tail, let's go ahead and look at this. All right, so here I have head and tail. You can see the numbers, the labels are just randomly interspersed here. And we created these with this make blobs function that came from the sklearn datasets. So I'm not going to necessarily review this, except just to mention that we're making these distributions, these clusters that are labeled. And we've created a new data frame here, and you can just look at the head or the tail, or you can sample maybe 10 data rows from that just to look at the different data points. Now normally we would scale this as well, but these are already fairly well scaled, so we can probably skip that step. Alright, let's go ahead and just break this into our training data. And so what I'm going to do is just take the first 80, alright, and then create a copy of that, so it isn't just a slice of the data frame, but it's actually a copy that stands alone. Okay, and then I can see head, and I can also print things like the length of data. Oh, and the length of train. Alright, so that's just the first 80 rows. Now let's do the same thing for test as well. Alright, and that's just going to be the rest of it, and I can just do 80 onward. And if I do test.head, one of the things I'll notice is that the index starts with 80. Now that's not a problem, but I typically just like to reset the index. So what I'll do is just do test equals test dot, and then I can do reset index, and if I just leave everything else out, no other arguments there, and do head, then I'll see that it dropped the index and reset it to 0 up through 19. There are going to be 20 data points in there, and it put this new column in here, okay, this new index. So if I don't want that, then I can just say drop equals true, and it will just drop that, so I no longer have index in there. Alright, so I've created these two, and now what I want to do is just go ahead and print the length of both of these, train and length of test. Alright, so I have it 80, 20, 80 for my training data set and 20 for my test set. Alright, let's go on to the next one. I'm going to insert a cell below. Now what I want to do is just take a first test set. Alright, so the way I'm going to do that is, let's just go ahead and do test, and I'm going to get the very first one, which is just 0. Alright, that's going to be my very first row. There's my x, y, and z. And let's just go ahead and test this one, and then we'll set it up as a loop later. Alright, the very first thing I want to do is just calculate a list of distances, and I want to go through all of the rows in the training data set. So that's going to be for I in range, and then that's going to be length of train. That'd be 80 rows that we're going to be going through. And then what I want to do is calculate the distance. And one way you can do that is with the linalg norm, okay, function, but I'm just going to go ahead and write it out without that function. Alright, and I'm going to just say x2 equals, and then we're going to take the difference, we'll square it, and then we'll add up those squares and then take the square root, okay, to get the distance. So this, what I want to do is, let's just call this, so it shortens it a little bit, t equals test of just the first row, and let's calculate all these distances. So what I'm going to have is, it's going to be the test minus the train. Alright, and I want to get just the x value from that, and I'll do just the ith row. Alright, and that one I'm going to square. And then I want to get the distance to y as well. I'll just copy this. So this is going to be my difference squared. Now here I have to do x as well. Okay, and then this one is going to be y. Alright, so I have my difference. Let me just go ahead and run this, make sure there's no errors there. Alright, and then my distance is going, I'm going to append a distance here. And let's go ahead and just do square root of x2 plus y2. Alright, now you probably got an error that numpy is not defined. So we can just add that at the very beginning with import numpy as mp. It's just a shortened name for numpy. Alright, I'm going to just go ahead and run this again. Alright, and let's get all these distances. We can just print them out. Here's all the distances. Now these are 80 values right here. We want to take just the top 3, let's say just 3 values. Alright, so let's say that k equals 3. That's our nearest neighbors. Alright, so the way that I can do this is do sort, and if I print that, then I can see the lowest. Oh, I don't have a sort. Okay, what I'm going to do is just add it to the data frame. Let's do this. I'm going to add it to the train data frame. Alright, and that's going to be equal to d. And then what I can do is train dot, and then I'm going to sort values, and I'll sort by d. Alright, and let me go ahead and just print the head of that. Alright, so there are the top 5 values with the lowest distances. Now let's say we just want the top 3, then I would just do head 3. Okay, so I could do k here and get the top values. Okay, so the other thing that I can do now is let's go ahead and just save this. We'll save this out, and then we can take the mode of it to get just the top 3 z values, and that's going to become the new label for this test row right here. So I've taken and sorted the distance to the x and y values, and then I'm going to use these three from the training data to assign the label to this test set. Alright, so I've got all of these. One of the things that I can do is, okay, I've sorted these, and then I can just take the mode. Alright, and I'll just call that M. And then let me print M. Okay, so let's see, the mode is going to be, I guess what I need to do is just take the 0th value of that. Okay, so I'm doing too many things in one row right here. Let me just break that down just a little bit more. Okay, so I'm going to take and go ahead and get my distance that is, okay, I'm going to use just 0 to k, and so I'm going to do a train after I've sorted these. Okay, this is my distance. Okay, let's just get a sorted data frame here. And that's going to be this new train, and I'm going to sort the values, and I'll sort them by D. Alright, and then after that I'm just going to take the mode of that. So if I have S data and then the mode, then M mode equals S data, and I'm just going to take the Z values. That's what I needed to do before. I location 0 to k, I'll just take the first k values, and then I'll calculate the mode. And then if I print M, then I'm going to get just a data frame. I just want to take this value right here. So what I can do is just say just the very first value. Okay, and then I get 1. Alright, and let's go ahead and append that to a list. So now what I'm going to do is, instead of just testing this one, let's go ahead and run through a loop and do all of our tests. Okay, so now I'm going to need to create a new loop here. So I'll just say the result is going to be C for all of my tests. And I'll do for j in range, and we'll do length of my test set. And then everything needs to come inside this loop. So I'm going to have a nested loop here. And now I'm going to make this j. And then these will update each cycle through to be a new test set. Okay, I've stored the mode here, but now let me go ahead and just append that to this list C. So I'll just go ahead and say that C.append, and we'll append that M value, the mode that we had. Okay, at the very end, let's go ahead and just put this into the test set, and we'll just assign that. Alright, and then we'll print test head. So now we have the label, the true label, and then also the predicted label. Okay, and then what we're going to do is, now that we've done the kNearest neighbors calculation, we need to evaluate it. So let's go ahead and insert a cell below, and there's a couple different ways to do this. I'm going to show you the sklearn metrics way of doing this, and we'll import confusion matrix. And my confusion matrix is going to be equal to confusion matrix, and then we want to give it the test set with the true labels, and then also the test set with the predicted labels. And if I run this, then I print CM. That's going to show me the confusion matrix. This is the where I predicted correctly and predicted correctly. Okay, for the z values for 0 or 1. Okay, now let's go ahead and do one other thing with this, calculate the accuracy as well. So the accuracy is going to be the trace of this, the sum of all the diagonal elements divided by the summation of all of the values in here. So we had 20 values, and we're going to do the trace divided by the length of the test. So accuracy is going to be equal to np.trace of the confusion matrix divided by the length of the test set. And then I can print accuracy. You can put that in percent or just have it in fractional form, but we had 100% accuracy with this set. Alright, so that's great, but maybe we want to generate a confusion matrix as well. So let's use pandas to do that. I'm going to have maybe the confusion matrix. I'll just reassign this PD crosstab. Okay, I'll have my test, and these are the true labels, and then my predicted labels. Alright, and let's just go ahead and print CM, and you can see that also gives you the confusion matrix. But let's go ahead and display this now instead. And so I'm going to use Seaborn, and that's SNS, and I'll generate a heat map, and I'll have my confusion matrix, and I'll annotate, set that equal to true. So this generates a confusion matrix. If you'd like to save it, we can do plt savefig, and then maybe we call it confusion matrix.png, and you could even change the dots per inch to maybe a little bit higher. And then you'll see that it generated a figure for you. You can save that and paste it into a presentation. Alright, so that's it on the Python code. We've done quite a few things here, but started with this generated data that came from sklearn. We split into a train and test set, and then this is our kNearest neighbors algorithm right here. If you use the np linalg norm function, you could condense this maybe into one line. And then I've just kept track of, in this case, the mode, or the most common label with C, and then also the distances with D. And we sorted that list by D, and then I just took the K elements, calculated the mode, and we assigned that to M and appended that to our list C. Right, and then once we had all of the calculations done, then we went on to the confusion matrix, calculated the accuracy, and also a graphical representation with the confusion matrix. Alright, well, I hope this helped. I'll put this content here on this page, and there's also a little bit more with calculating with some of these figures and also with number identification as well, if you'd like to check that out.